Good morning all. In this class, we are going to discuss about introduction to proofs, various proof methods and proof strategy. So first, before going to discuss about proofs, first we should learn about some basic terminology. So first we should know what is a theorem. So we can define a theorem as a statement that is shown to be true. Next, we should discuss about lemma. What is a lemma? So we can define a lemma as a less important theorem that is useful in proving another theorem. It is nothing but a lemma. Next, we should know about corollary. So what is a corollary? So we can define a corollary as a theorem that can be established directly from another theorem. That is nothing but a corollary. Next, we should discuss about axiom. Axiom, which is also called as a postulate. So we can define an axiom as the statements that are assumed to be true. Next, we discuss about proof. What is a proof? So we can define a proof as a valid argument that establishes truth of the statement. Along with this, we should know some basic definitions which are helpful in proving some theorems. First, we should know what is an even integer. When can we say that an integer is even? So we can say that an integer is even if there exists an integer k such that n equal 2 into k. That means if we are able to express an integer in terms of multiples of 2, then that number will be an even integer. Next, we should know about odd integer. When can we say that an integer is odd? If we are able to express in the term of 2k plus 1, then that integer is said to be an odd integer. Next, perfect square. When can we say that a number is perfect square? For example, if you take an integer a, we can say that a is a perfect square if a can be expressed in the form of a equaled b square, where b is some integer. If you are able to express integer a in the form of square of some integer, then it is called a perfect square. Next, we should know about rational number. When can we say that a number is rational? If we are able to express in the term of p by q, where q is non-zero, such number is said to be rational number. Trivial proof. Now, while we are going to discuss about proofs, first we should know what is a trivial proof. So when we want to prove that p implies q is true, it is enough if we show that q is true, because know the truth table p implies q. As there are two different variables, in this table we will have 4 columns. One is both true, true false, false true, false false. We know that implication for only one case it will be false. That is when p is true and q is false. In that case only p implication will be false. In all remaining cases it will be true. So if we observe from the truth table, we can understand that whenever q is true, irrespective of p value, the implication is getting true. That's why if we want to prove that p implies q is true, it is enough to show that q is true. Then obviously it will be true. Such proof is called trivial proof. Take one example. If there are 100 students enrolled in this course, then 6 square equal 36. In this example, we will assume p as there are 100 students enrolled in this class. 100 students enrolled in this course. We will assume q as this one. Assume q as 6 square equal 36. Here we want to prove that p implies q. As it is trivial, it is enough if we say that q is true. What is q here? 6 square equal 36. We know that it is true. So as q is true, we can say that the theorem is trivially true. So we can say that trivial proof means when we want to prove P implies Q is true, it is enough if we show that Q is true. Such proofs are called as trivial proofs. One more example is here. If x square minus 5x minus 1 greater than or equal to 0, then we have to prove this one. X minus 1 into x minus 3 greater than or equal to minus 2. We have to prove this. As we know that in case of trivial case, it is enough if we prove that Q is true. What is P here? X cube minus 5x minus 1 greater than or equal to 0. That is considered as P. This part is considered as Q. So, if we want to prove this result, it is enough if we prove that x minus 1 into x minus 3 greater than or equal to minus 2. Now, by considering this part, we can prove that whether it is true or false. Consider x minus 1 into x minus 3 greater than or equal to minus 2. We will prove this one. If we multiply this one, then we will get x square minus 3x minus x plus 3 greater than or equal to minus 2. That implies x square minus 4x plus 3 greater than or equal to minus 2. Take minus 2 to the left side. Then we will get x square minus 4x plus 5 greater than or equal to 0. We will write it as x square minus 4x plus 4 plus 1. 5 can be written as 4 plus 1. So, we can write like this. See the first part, x square minus 4x plus 4. It is in the form a square minus 2ab plus b square. It is in the form. So, apply a minus b whole square formula. That implies x minus 2 whole square plus 1 greater than or equal to 0. So, x minus 2 whole square, it is obviously positive. Whatever the value of x, as it is square, it is positive. Positive plus 1, which is always positive. So, this condition is true. So, we proved that x minus 1 into x minus 3 greater than or equal to minus 2 is true. So, as we proved that Q is true, hence we can say that it is trivially true. Next we will discuss about Weier's proof. So what is a Weier's proof? So if we want to prove that P implies Q is true, it is enough if we show that P is false. We know that P implies Q will be false only when P is true and Q is false. In that case only, implication will be false. In all remaining cases, it will be true. That means whenever P is F, whether Q is true or false, whatever it may be, it will be true. So, in order to prove the theorem using Weier's, it is enough if we show that P is false. Here consider one example. If P is a prime number, if 6 is a prime number, then 6 square equal 30. Here 6 is a prime means P. 6 square equal 30 means Q. So here we want to prove P implies Q. So we can say that it is true if P is false. What is P here? 6 is prime. It is clear that 6 is not a prime number. So obviously P is false. So as P is false, clearly we can say that the theorem is proved Weier'sly. So this is one example for Weier's proof. Take one more example. N plus 1 by n less than 2. Then n square plus 1 by n square is less than 4. So this part is considered as P. This part is Q. See the first one, n plus 1 by n less than 2. Then this condition also will be satisfied. N square plus 1 by n is less than 2. So take the denominator to right side. Then it will become n square plus 1 less than 2n. Take 2n to left side. Then we will get n square minus 2n plus 1 is less than 0. This is nothing but n minus 1 whole square. which is less than 0. That is false, because take any square, even though we take n as negative value, as it is square, it must be positive. But here we got that it is negative. That means our assumption is wrong. So we proved that n plus 1 by n less than 2 is wrong. As we proved that P is false, by Vacuous proof, we say that our condition is true. So this is one example for Vacuous proof. Next, we will discuss about direct proof. So what is a direct proof? So we can say that whenever we want to prove that P implies Q is true, first we will assume that P is true, and after using some axioms, definitions and previously proved theorems, we should prove that Q is also true. Then it is a direct proof. So in case of direct proof, whenever we want to show that P implies Q is true, first we must begin with assumption that P is true, and after application of various axioms, previous theorems, we should be able to derive Q is also true. Then the theorem is proved. See, consider one example. Use direct proof to show that every odd integer is difference of two square numbers. This we have to show. For example, see this one. Suppose n is an odd integer. So first we are assuming that n is an odd integer. So as n is an odd integer, by the definition of odd integer, n can be expressed as 2 into k plus 1, where k is an integer. So by the definition of odd integer, n can be expressed as 2 into k plus 1, where k is an integer. So what is the problem? We have to prove that difference of two numbers is an odd integer. So consider k plus 1 whole square minus k square. So what is k plus a plus b whole square formula? A square plus b square plus 2ab. Apply that formula. K square plus 2k plus 1 minus k square. Plus k square minus k square gets cancelled. So we got 2 into k plus 1. So we know that 2k plus 1 is equal to n. So instead of this 2k plus 1, we can write n. So we proved that k plus 1 whole square minus k square equal n. That means we proved that n is the difference of two squares. This is the example for direct method. See the one more example. Here what we have to prove is, if n is an odd integer, then 5n plus 3 is even integer. That we have to prove. So assume n is odd. So first we will assume that n is odd. So by the definition of odd integer, we can write as n equal 2k plus 1. So what we have to prove? We have to prove that 5n plus 3 is even. So consider 5n plus 3. So we will consider 5 into n plus 3. So in place of n, substitute 2k plus 1. So 2k plus 1 plus 3. So if you expand it, we will get 10k plus 5 plus 3. So it is nothing but 10k plus 8. So from these two, we will take 2 as common. So we will get 2 into 5k plus 4. If we assume 5k plus 4 as t, it is nothing in the form of 2 into t. So it is a multiple of 2. As it is a multiple of 2, it will be even. So what we proved that by taking n is an odd integer, we proved that 5n plus 3 is even. So this is an example for direct proof. Take one more example. What we have to prove is, if m plus n and n plus p are two even integers, then m plus p is also even. This we have to prove. So first this take two parts, m plus n and n plus p. If m plus n and n plus p are even integers, we should prove that m plus p is also even. So first we will assume that m plus n is even. So if m plus n is even, so by the definition of even integer, we can write m plus n as m plus n equal some 2 into some s, where s is an integer. Similarly, we assumed that n plus p is also even. So by the definition of even integer, we can write n plus p as 2 into some integer t. So by the definition of even integer, m plus n and n plus p are expanded like 2s and 2t. Now sum them. So m plus n plus p equal 2 into s plus 2 into t. See the left side, m plus p plus 2n equal 2s plus 2t. Take 2n to the right side. Then we will get m plus p equal 2s plus 2t minus 2n. So take 2 as common. Then we will get s plus t minus n. So m plus p is equivalent to 2 into s plus t minus n, which is a multiple of 2. That means we proved that m plus p is even. So by taking that m plus n and n plus p as even integers, we proved that m plus p is also even. So in this way, we can prove this example.